Well, from throwing things to judging, and one of the most interesting collections of mathematical problems that sport has to offer are issues of scoring systems and judging. And if you want weird judging, then it's got to be ice skating. So my daughter is a professional ice skating coach, so I sort of get lots of information on the inside about all this craziness. Of course, the rules changed after the Olympics at Salt Lake City because something very outrageous happened. And I'm going to show you what that is. Well, actually, two things that were very outrageous happened. The second thing I'm not going to talk about was not to do with mathematics. It was simply cheating by judges. But what the strange thing was simply the appearance of a classic voting paradox of the sort that we understand in the mathematics of voting and economic preferences actually emerging and determining the gold medalist in the women's figure skating. So there are probably some things that you don't know about skating scoring, or at least how it used to be. So you remember all those 6.0s and 5.9s that everybody gets very excited about. They don't count for anything. So if everyone skates and they get those scores are not carried forward. All they do is determine your position in that competition. So if you score 6.0 from every judge and the second competitor scores 2.0, you don't get any extra credit there except that you're first and they're second. So it doesn't matter by how much you were better than the second performer. So that was the first classic blunder that a mathematician could have told them not to do. So here's the situation in the Olympic women's figure skating, and these were the top four competitors: Kwan, American Hughes, and Cohen and Slutskaya. And the way it worked, you first of all skate a short program, and if you're the best skater with the highest score, they give you half a point. And if you're the second best, they give you 1. If you're third best, 1.5, and if you're the fourth best, 2. So it's as though they are using rankings as the score, but they halve them. So that when you do the long program, you get more credit because it's longer, it has more ingredients. So if you win the long program, you'll be given a score of 1.0. Then they'll add those two scores together, and the skater with the smallest score will be the winner. Okay, it all sounds very easy. But of course it turns into a disaster. So here are the outcomes from the short program, and then these three skaters skate in the long program. And after they've skated, the best performance is by Hughes. And so she's riding there with a 1.0, and the second best score is by Michelle Kwan, she's 2.0, and the third is the young American Cohen with 3.0. So at the moment, if we add the scores up, Kwan is in the lead overall, Hughes is second with 3.0, Cohen is third with 4.5. Slutskaya had been second in the first round. She then skates. What happens? So notice Kwan is ahead of Hughes. Okay? Well, Slutskaya skates and is the second best in the long program. So that shunts Kwan down to 3 and Cohen to 4. If we add the scores up, Hughes and Slutskaya are now first. That degeneracy is resolved in skating by first taking the best performance in the long program. So Hughes wins the gold medal because she was better than Slutskaya in the long program. But look what's happened. Kwan was ahead of Hughes, but after Slutskaya skated, Hughes is now ahead of Kwan. So the performance of Hughes has changed the relative positioning of Hughes and Kwan. So this is a situation that usually in voting scenarios you tend to exclude by an axiom at the beginning. It's like the joke about the philosopher who goes to a restaurant and the waitress comes around and says that we have beef or fish, what would you like? And the philosopher says, I'll have fish. and then a few minutes later the waitress comes back and says, we've got an extra thing on the menu, we've got pork, would you like to change your order? And he says, yes, I will, I'll have beef. So this is the first time this paradox had sort of emerged and actually determined the gold medal in a high-profile event. And at root, the problem is one that mathematicians understand quite well. You mustn't add preferences. Okay, they're non-transitive. If you had kept all the 5.9s and the 6s and so forth, if you just added all those together over the 2 rounds of the skating, you would have got a far superior system of judging the results. So at root, the paradox that's happened here is simply that if you have 3 people and they want to decide amongst themselves which car we should buy. So they may be students, they're all putting in money. Somebody wants to buy the Audi, A, somebody wants to buy the BMW, B, somebody else wants to buy the Cortina, C. And so they say, right, well, we're going to vote, each put down your preferences, and the first student's preference is Audi, then BMW, then Cortina. The second student is BMW, then Cortina, then Audi. And the third student wants the Cortina, second choice is the Audi, and third the BMW. So what happens if we look at these preferences? Well, the Audi is preferred to the BMW 2 to 1. The BMW is preferred to the Cortina 2 to 1. But the Cortina is preferred to the Audi by 2 to 1. So the preferences are non-transitive. You mustn't add preferences. And you'll recognise this paradox emerging if you sit in little academic and departmental committee meetings where you take votes on things. So the astute mathematical chairman will try to exploit this type of paradox whenever he or she can. Well, let's move on to a simple example of sort of probability and scoring. And this is a problem that you can deal with in a sophisticated way as you wish. This is the simplest way to do it. And it's really asking the question, is the Premier League in England just a random process? You know, do we need to go to all the expense and the trouble and the policing of actually playing the games? You know, could we just replace it by some simple algorithmic device? I mean, when the weather is bad, it's replaced by the pools panel. So why not have the pools panel every week and just run it in a random way? Yeah, so my wife thinks this is a marvellous solution and can't really understand why people haven't latched onto it before. Well, what happens in the Premier League? There are 20 teams and they each play all the other 19 teams twice. So they each play 38 games. If you look at football statistics, sort of in the large, over long periods of time, different countries, there's one pretty stable statistic. About 1 game in 4 is a draw. Okay, so let's assume that the probability of a draw is a quarter. And for simplicity, we'll apportion the remaining 3/4 of the probability sort of equally between home and away wins. So in any game, there's a 3/8 probability of a home win and a 3/8 probability of an away win. Now, we could, if we just had an 8-sided spinner, play all these games, you know, sort of thing we used to do at school with funny little dice, and you could generate a random set of results, labelling your teams A, B, C, D, or whatever for all 20 of them. Or you can put it on a computer and a few seconds later it will generate for you all the results and a league table where the team that randomly ends up with the most points we'll call team number 1. We don't have to call it Arsenal or anyone else, but let's call it team number 1. And so what you're seeing here in red is the randomly generated Premier League table from our simple model. Probability of a quarter for a draw, 3/8 for home, 3/8 for away win. And when I prepared this slide, I just picked some past league result of the table. I just picked one where Manchester United didn't win, but Wolves are at the bottom, and they still are almost, aren't they? And what you notice about this, so up at the top here, this is all the usual suspects, Arsenal, Manchester United and Chelsea. The fourth team that year were Liverpool, who were actually closer to being relegated than they were to winning the league, even though they were in fourth position. And what you notice is that from 4 downwards, the random model really is a very, very good fit to the points distribution in the league. The top 3 teams, of course, are operating with a much higher probability of winning a game than our simple 3/8 at home and 3/8 away. I mean, Arsenal are winning 70% of the games they play that season. So this is a pretty uncompetitive league that year. Everything else here, you don't have to bother with most of these games. If you look more closely at this, you can see how you would make this model better. Down the bottom, the random model works pretty well. Up near the top, after the first 3, it's also pretty good. In the middle, it starts to deviate quite a bit. So why is that? Well, my guess, I think it's simply that if you're one of the top teams, it doesn't matter whether you're home or away, you win all the time. If you're one of the bottom teams, doesn't matter whether you're home or away either. You lose all the games. But if you're in the middle, you tend to win at home much more often than you win away. So our simple assumption of the same probability for a home and away win is not good. And that's what you would work on next to create a better model. Well, that's a simple example of scoring. Something that's a bit more sophisticated. If you look across sports, there's very complicated systems of scoring. You know, in the old days, in squash and volleyball, you only scored a point if you won a point when you were serving. So if you weren't serving, you'd have to win the next point to get serve, and then you would have to win again in order to score a point. The rules are changed now, and you get a point just for winning the rally, whether you're serving or not. So that's mathematically unfortunate because it was an interesting situation. In squash, there used to be a rule that if you were at 8-all and you were receiving, you could elect to play to 9 or to 10. So what should you do? Well, roughly you can see is that if you're not a very good player and you're really rather lucky to be at 8-all, you should play to 9. Because you might fluke 1 more point, but your chances of fluking 2 more are much lower. When you subject this little mathematical problem to a little bit of analysis, not entirely trivial, you find that if your probability of winning a point is bigger than 0.36, you should play to 10. But if it's less than 0.36, you should play to 9. But some sports like table tennis have changed their point scoring system recently. Well, I say recently, several years ago. If you play table tennis in the garage or at home, I bet you're still playing under the old rules. You're playing up to 21, best of 3 sets. But the real players, okay, the ones that don't play in your garage, the ones that are trying to win the Olympic Games, they play to 11. And they play best of 7 sets, and they just sort of have 2 serves rather than 5. So the rules were changed in this way to reduce the amount of time spent on long, rather one-sided games, and to reduce the effect of being the server, so that you didn't end up at 16 or 17 all, and then one of the players finds they're serving, and that really tips the scale so that they win the game. At Cambridge, we've had, I think she left a year or so ago, a year or 2 ago, we had the world's best ever table tennis player as a sort of master, PhD student. So a Chinese woman who retired when she was 24 with 4 Olympic gold medals and I think 15 world championships, and was voted China's athlete of the millennium, I think, and was the deputy leader of their delegation at the Beijing Games, and I suspect might well be the leader in London. And she would occasionally, I think, play in and come out of retirement to play in intercollegiate competition or the local league. I never found anyone who'd even seen the ball, actually. So what one wants to know in games like table tennis is really what's the reward for skill versus luck? If you just played a game of table tennis with 1 point, okay, or if you just tossed the coin at the beginning, didn't play any points, okay, there would be no reward for skill really at all if you just tossed the coin. If you played just 1 point and the whole match was decided, again, if you're the weaker player, you've got a much bigger chance of just fluking that point and winning it. So the more points you play, the more skill is going to win out over luck. But you can't keep playing forever. So how many points do you need to play so that 2 evenly matched players will produce a result where skill will tend to determine the winner rather than luck? So let's take a simple model again. Suppose that you're playing a game like table tennis and the probability of winning a point is P. Okay? Well, you can go back and sort of change this to a slightly different probability if you're receiving or serving and so on. But let's see what happens if it's P. And let's suppose we're in top-level table tennis, so there's evenly matched opponents. Okay? So P is very close to a half. So we'll call it half plus a little bit S, where S is much, much less than a half. Then this is just like a series of sort of Bernoulli trials, of random trials, and if there are n, if you have to get to n points, where n might be 21 or 11 or something else, to win the game, then the probability criterion is that you want to win n points before you lose n points. And so you just work out the sum of the probabilities from the Bernoulli trials, approximate to the probability being close to a half, get rid of all the factorials using Stirling's approximation, and what you end up with is that the probability of winning n points before you lose n points is a half plus twice this little bias times the square root of the number of points over pi. So this is interesting. It has many features that you would expect. Okay, if S is 0, so they're perfectly matched opponents, then Q is a half also. But as S gets a little bit bigger than 0, so the chance of the n points being won grows with S. Okay, so the more games, more points you play, the greater the chance of skill winning out over luck. But the number of games, the number of points you have to contest goes like the square root of n over pi. So suppose that you're contesting each game by n points, so n could be 21 or 11, and then you're saying we'll play m games. Okay? So if it's best of 3, you need to win 2. Sorry, m is the number of games you need to win in order to win the whole match. So best of 3, m is 2, best of 5, m is 3, and so on. Well, you need to apply this twice. So first of all, to win any one game, okay, your marginal advantage would be 2 sort of s dash, say, times root m over pi, but your s dash would be the 2s times root n over pi from winning the points in the game. So you fold those two formulae together, and your overall probability of winning the whole match, okay, is 4s over pi times the square root of m times n. Okay, so that's the key factor. So if you were playing under the old rules of table tennis, then n would be 21, and you would need to win 2 games, okay, best of 3. So m times n is 42. The change of rules, where you're best of 7 and you play each game to 11 points, m is 4 and n is 11, and the product is 44. So it's very interesting. You begin to wonder whether somebody who knows something about mathematical statistics had something to do with changing the rules. Because the product of M and M are really very, very similar under the two systems. Okay? If under the new rules you paid best of 3, okay, M times M would be 22. And the reward of luck compared with skill would be twice as great as it was under the old rules. So you can use this type of consideration, all sorts of games, to evaluate the relative role of skill versus luck.